We are very pleased to have David Bergman. He kind of, in fact, saved our AMS seminar because we didn't have anybody coming over next week, so we kind of scheduled it this week. David was here. He agreed to give a talk. It's a real pleasure. So David completed his PhD from Carnegie Mellon in the ACO program 2013. And since then, he has been at University of Connecticut as an assistant professor. He's doing splendidly there. He mostly works on discrete optimization. He has this interesting take of using constraint programming on discrete optimization problems, and he's recently, or maybe ever since CMU, I don't know when you started venturing into nonlinear stuff.
A couple of years ago or so, yeah.
So it's going to be some nonlinear discrete optimization. So take it away.
Thank you very much. Thank you very much for having me here. Good to see people that I know and new people. Hopefully I can meet all of you. Yeah, I definitely make this as dynamic of a interaction with the audience, asking questions. More than happy to dive into anything. I'll be talking about discrete nonlinear optimization by state space decompositions. This is joint work with a close colleague of mine, Andre Zire. I think if you look at both of our CVs, 70% of our publications are with each other, but that's good, right? We're able to kind of push this idea forward, and hopefully other people will start using it as well. This paper was accepted for publication in Management Science a couple months ago. So before I go into actually the meat of this talk, let me talk about what decision diagrams are, which is the basis of this work. So what is a decision diagram? This is something actually from the CS community, Randy Bryan actually at CMU, right? And it's been used for a lot of things classically, but what we do in this body of work is use it as a graphical representation of solutions to a discrete optimization problem. Okay, so here is a particular discrete optimization problem. All the variables in this talk will be binary by assumption. These things do extend to general integer cases, but not to continuous variables. So we're in the world of discrete, and in particular binary variables. So here we have three variables, x1, x2, x3. There have to be some less than or equal to 2, so basically they can't just all be 1. And then we have some nonlinear function here. Really, if you think about it, it's a linear function divided by 1 minus that linear function. Okay? And this is what I would call a decision diagram for this problem. Directed acyclic graph, you think of the arcs as pointing downward. Each layer corresponds to a problem variable. Dashed arcs set the variable equal to 0. Solid arcs set the variable equal to 1. In this way, if you take any path from the root to the terminal, you are encoding a solution to your problem. So this path says take x1, set it equal to 1. Take x2, set it equal to 0. Take x3 and set it equal to 1. Okay? If you look at this, this graph from the root to the terminal, you can easily count the number of paths. It's 7. 7 solutions to this problem, all is fine. You could build a much more compact diagram if you just care about the constraint set to represent all the set of solutions. That's no problem. But we want to also encode through the lengths from the root to the terminal the value of the objective function for the solution that you're plugging in. Classically, we've used this for linear optimization problems, and in this case, that's quite easy. Because if you think about what's the impact of setting a variable equal to 1, it's just that linear function, that's it. At 0, it's just 0. For nonlinear optimization, it gets a little bit trickier, right? Because I can't, for example, say that on a given layer, the impact of setting x2 equal to 1 is going to be the same. And even 0, I can't have an impact, depending on the problem that you're talking about. But in this case, this is what I would call an exact decision diagram for the problem that you see on your left. Again, there's still 7 paths here. I haven't changed the feasible set of this diagram. But if you take any path and you add up the arc costs, you will get exactly what the function evaluates to. So here again, we're looking at this solution x prime 101. So x1. Yeah?
So should we assume that the objective function are rational functions of the variable, or any nonlinear function?
Any nonlinear function actually is fine. At this point, we are considering just binary variables. So it doesn't have to be rational. It can be, you can have square roots, you can have all different types of things. Later in the talk, I'll talk about how we can actually handle submodular functions. If these are set functions, you can think of them as binary optimization. We can do these supermodular, whether you're maximizing or minimizing. And so yeah, we'll talk about some of those. But this is one example, and it's kind of nice when you have a function which is of the form of ax, and then it's a function on top of ax. So then you can, if it's a convex function that you're talking about, you can kind of prove whether it's supermodular, submodular, whatever. But anyway, this is an exact decision diagram. You take the path from the root to the terminal, you add up the weights. That's exactly what you get when you plug in those values into this function. Okay. Any questions on what this diagram is? Of course, we have to talk about how to build it and how to actually use it in practice, but this is what I mean by a decision diagram for the purpose of this talk.
So for now, your feasible region is just going to be linear constraints with binary variables.
For now, that's what we're considering. Linear constraints.
So this diagram could be huge.
It is going to be massive, but we can handle it in different ways. So the way that this talk will go is I'll first talk about the decomposition that you might want to use for a nonlinear problem.
Okay.
And I'll go through that, and we'll talk about how we do that. And then for each term, we're going to build one of these diagrams. Eventually, we'll get to the point where we're like, this is too huge, what do we do? And then we talk about relaxations, restrictions, and all these things. Yeah, I mean, it'd be crazy to think that this thing is going to be compact, because then you've solved the problem. It's obviously not possible. Okay, cool. So this particular paper, the contributions are the following. We propose an integrated approach to solving nonlinear discrete optimization problems. We will assume, as you said, that the constraints for now are linear, although I think that we can release that assumption as something that we are working on, so you can maybe set up the constraints that are nonlinear using diagrams, but that's not in this particular paper. So we're going to use the decision diagrams to model the nonlinear functions in the objective function, and then use integer programming to solve over that diagram when you have other constraints that are interplaying. And actually, we're going to have multiple decision diagrams, not just one, partially because each one's going to blow up, so if you have many little ones, you might be able to handle it, but also because you are going to assume that there's some kind of decomposition to your problem. And then we're going to, along with doing this, you have to talk about how you build these things. And the way that we build them is through recursive models. And we have several general recursive models for nonlinear functions. What I really like about this particular paper is that we can handle, for example, submodular and supermodular, maximizing and minimizing. And actually, if you can decompose it so that this part of your objective function is submodular, this part is supermodular, and you're maximizing or minimizing, it doesn't matter, we can kind of handle that problem, right? So I think it's, that's what I really like about this particular approach. And we apply the techniques to real-world optimization problems. Actually, we just find some problems in the literature and solve them. Okay, cool. So how do we do this? It's an integration of integer programming, integer linear programming, I should say, and decision diagrams. The idea is that the decision diagrams will provide linearizations of the objective function terms, and then integer programming will deal with the constraints and solving over the diagrams concurrently. So we assume that we have this kind of structure. X is in 0, 1, you have some linear constraints, and then we have an objective function. You can have just one term here if cap is 1, but cap can be some integer. And each one of these terms in the objective function is nonlinear. Can be linear as well, of course. That will just allow integer programming to deal with. But for every nonlinear term in the objective function, we are going to create one of these diagrams. So we're going to have a set of diagrams. We're going to have a set of linear constraints. And what we do is we reformulate the problem as a consistent path problem. What are we going to have to do? As you'll see later on in the talk, you're going to have a series of these diagrams. What you're going to have to ensure is that the assignments in this diagram are equivalent to the assignments in this diagram, or at least are consistent with the other ones, consistent with the other ones, consistent with the other ones, and then you optimize your objective function. And we'll talk about how to do that, and the goal will be, again, to assign the variables that are consistent and have the maximum total length.
Quick question.
Yes?
So is there any assumption on the subends fk? I mean, is there a particular basis in which these functions are being expanded, or no assumption?
We aren't making any assumptions right now. Of course, the way that we build the diagram has an inherent, we prove that you can do this for certain structured functions, right? There are some functions that we can't, or we don't know how to do it yet for. So you can always build it, but it's just going to grow too large and we're not going to know how to deal with it if it's something really, really complex. We're going to build this with recursive models. So as you'll see, we actually, we're going to get to that a lot later on. Yes.
So you're saying you can only build these diagrams for a specific class of functions. And if the overall function is somehow a sum of functions from these different classes, then you can handle it.
That's exactly right.
That's what you're trying to say.
Yes, exactly. And I think that even if it's not one of the functional forms that we're talking about in this talk, because we're talking about recursive models, which are a little bit different, right? Then we can actually handle them. It's just harder to build what we call relaxations and restrictions. Because if you don't have any kind of structure on these Fs at all, these things are really going to, not only they're going to blow up, we're not going to know how to compact the diagram in a controlled way. You'll see what I mean by relaxations and restrictions a little later on. Yes, and so, great question.
Are we typically thinking about a large kappa or a large n?
Yeah, it can be quite big. I mean, of course, these are really difficult problems, so we're not talking about thousands of variables and thousands of terms, but we are talking about maybe 50 to 100 variables, and you can go up to, depending on the problem itself, 50 terms, 100 terms. Yeah. So, actually, Alper Turk was here, I think. I was just talking to Amitabh about that a couple weeks ago. And so one of the problems that we studied was a mean risk portfolio optimization problem that he proposed. We generalized it to have higher order terms. I'm going to talk about that later on. But just to show you for that particular, just to show you some of the results that we get. If you use this decomposition by BDDs and we compare with other nonlinear solvers, right? Barron and Skip are kind of what I would consider the best nonlinear solvers for general, even convex or whatever, nonlinear discrete optimization problems. We're able to solve many, many more instances in a given time period. So portfolio, and this is time at a time, how many you're solving within that set of instances. And so we get results like this. Here's another problem, latent class loaded assortment problem. This is a product assortment problem. Again, comes from a paper in 2014. And yeah, I mean, by using these decision diagrams to enhance their branch and check framework, we're able to really solve many, many more instances faster. Okay, so let's dive a little bit deeper into the math behind these things. So you end up decomposing your objective function and construct decision diagrams. So both of those problems I showed, they have a natural decomposition. There's just a plus or a minus, and the terms kind of decompose that way. But you can come up with some, perhaps, more involved in non-apparent decomposition, and you reformulate the problem as a linear integer programming problem to find the maximum way consistent.
So, David, I have a quick, so I still don't understand what restriction you want to impose on the function, because it seems to me no matter what nonlinear, what function you have there, since your variables are only 0, 1, I can always create this decision diagram and put weights on the edges.
Absolutely.
So that the path length is exactly equal to the, so
totally possible. So the reason why.
So so let me ask you this. So are you asking, for example, what kind of functions can you represent with, let's say, a polynomial sized diagram like this?
Yeah. So there's two things involved. Number one, for a general function, you can always represent it, right? What I can do is I can just branch, and then the last arcs, just put the value of each one of those solutions.
Right.
Totally fine. One issue is that this thing is going to grow too large. Okay. What you can do when you are assuming some structure on these terms is you can find a way that as you're building this thing top down, find conditions in which I can merge nodes together, even though it's not going to be feasible to do so, but then I can create different arc lengths coming out that ensure that I'm getting a relaxation on my objective function. So you're going to build this thing top down, and I will have a bunch of examples, and then because of the structure that you impose on these individual terms and those objective functions, you're able to build a controlled sized relaxation. If each one of the terms are relaxed, then when you solve the integer programming problem that you get from the consistent path problem, you end up getting a global bound on it, and then you can use branch and bound. This is how it works. And that's why we impose the conditions. But in general, if you have very few variables for each of these things, you can just enumerate and put the thing together. And so in every example that we have in this paper, for each one of the terms that we're building the diagrams, let me make sure this is right. Yes, we are not, for any one of these problems, there is not a polynomial size exact decision diagram for it. You have to create these relaxations. The problem is for any arbitrary function, it will be very hard to figure out how to build the relaxation. When you impose some restriction on the functions themselves, it's easy to understand how you can build the relaxations.
But I could sort of turn the problem around and say, okay, let me actually try to classify or characterize the class of functions that I can represent using polynomial size things, and then prove some sort of an approximation result in the function world where I say that, okay, almost every continuous function is arbitrarily well approximated by this class that I have or something. Could you do something like this? Or?
Yeah, I mean, it's possible. We've thought about how to do this, right? It's really hard to prove how good your bounds are when you use these decision diagrams. We haven't had a very nice, I mean, there's one paper by John Hooker where he does it for scheduling problems. He does have some bound that you get when you approximate, but it's a pretty difficult thing to prove. But yeah, I'm sure that there's ways of doing it now. Because maybe if you take the function and you know you have some approximation that has some ratio, and then you build the diagram, you know it's polynomial, then maybe you already know that you have that bound or something. But yeah, it's a great point, something to investigate. Okay, so in order to just show what the diagrams are and how we build them, let's look at a concrete example. Again, this is from a paper by Alper. He looked at this mean risk optimization. So you think of this as n independent investments having an expected return mu and a standard deviation sigma. You end up with a function like this, where you're trying to maximize the first order term and minimize the second order term. This is kind of standard portfolio optimization. If you think of these as like fixed investment size, you have an AI times xi less than or equal to b, standard kind of knapsack constraint. And here you have a linear term and a nonlinear term. Okay? So these sigma squared I can just be a constant. It actually doesn't matter, but you do have a square root over this term. Okay? Now, in modern portfolio optimization, they actually consider higher order moments, not just the first and the second order moment. So in general, you want to maximize the first and the third order terms and minimize the second and the fourth order terms. The third order terms, skewness, fourth order kurtosis. So let's generalize the framework by Alper. Instead of just having expected return and standard deviation, you also have some skew and kurtosis. Now what do you end up with? You get a problem like this. Still you have this knapsack constraint. It's fine, it's linear. Each one of these terms, well this is linear, so let's not worry so much about that. But this is the square root function and negative, right? So square root function and negative, so it's like a convex thing. This is going to end up being a concave thing because it's got a positive coefficient. That's a convex thing. Okay? So this function is non-convex if you take the whole thing together. But each one of the terms individually are of that thing. Okay? So this is, let's see how we can handle something like this. What is the structure that we're imposing right now? Is that you have a linear function and then you have some convex or concave function on top of that linear function, for example. So what does the diagram look like in this case for this function? You end up with something like this. Take a solution, plug it in, you end up with the sum of the weights. That's going to equal whatever the function evaluates to. All right, just as before. Take another solution, 0, 0, 1, 1. This is another solution, x prime. If you just plug it in here, you get square root of 1 plus 3, and of course there's going to be some rounding issues perhaps, but yeah, you end up with 1 plus 1 in this case. All right? So every single solution corresponds to exactly what the function evaluates to. Okay, how do we build this thing? That's the first question. You build it via DP, dynamic programming recursion. Start from the top down, I think we were kind of getting to that already. You associate nodes, actions, states, transition function weights, and all different types of things. So there are many ways of building this diagram. You don't just have to build it top down. You can actually start with a full diagram of all the solutions in a single path, but 1 and 0 arcs, 1 and 0, and then expand it. That's possible. We have found that we get better diagrams when we build relaxations, which we're going to get to later on, when we build it top down. So the idea is you start at the root, you associate every node with some state, you then consider your actions just like you do in DP. In this case, the actions are just take a variable or don't take the variable. You think about the transition function, which takes you from a state to another state, and you think about the weight associated with that transition, which is essentially taking the function evaluated with that variable set to 1, and without that variable set to 1, based on your previous decisions, and put the weight in the diagram.
Sorry, just a quick question.
Yeah.
So is there any assumption made on how the function is presented? I mean, you could presumably imagine that the function, nonlinear function that you have, was presented as some multivariate polynomial because you're working over 0, 1. If I give you the function in that form as some multivariate polynomial, is it possible to infer the diagram from it?
You would have to translate it into a recursive model for that function. So whenever I go anywhere and I talk about these diagrams, whether it's this talk or a different one, people are like, okay, fine, but like, how do I know if a function is good for this diagram? And I don't know, actually. It depends on if it's got a good recursive model. Just like if you think about IP, you're like, here's IP, is it easy or hard? You just don't know. It depends on how good the linear relaxation is for that. It's the exact same thing here. You give me a function, if there is a good recursive model for that function, you've got a good diagram. If there is no good recursive model, don't use this technology or this approach. I think it's probably the best way to look at it. Yeah, but that's, yeah, and then this is something we're just coming to grips with too, right? I mean, it's really hard to tell which models are good for a solution technique. All right, so this is the general structure on each FK term. So we're not really looking at this binary variable model, it's a recursive model, okay? You start with some state s hat 0, set that equal to the root node state. And then for I equals 1 through n, you think about what is the effect or the transition of applying action xi to the previous state on the layer that you're at. That brings you to a new state. You then also can evaluate what the function returns. So if someone gave you this si, g, w formulation, it would be very easy to build a diagram. But that's not how we think about problems in general. I mean, at least not in the discrete optimization world. You typically have it over some binary variables, right? And so, yeah, so this WSX is the cost of applying action X at state S. And for any particular path, this will give you the total weight there. This is the resulting state after applying action X at state S. Let's look at our example and try to understand how we can formulate this problem or this particular function term in this recursive modeling framework. So the state space here, and this is not so difficult to see, I don't think. The state space is going to be what the base of the exponent is. So if I tell you what x1 plus x plus 2x2 plus x3 plus 3x4 equals, you can tell me what this function evaluates. So you just take that and evaluate the 1/3 or 1/2 power. And so the state itself, all you need to know in order to evaluate this function is what that inner linear term evaluates to. That's our state. Now what's a state transition function? So if I tell you that the partial sum is 4, and now I have applied an action of 0, what's going to be my new state? It's just going to be what it was before 4. But suppose now I've decided to take a variable, and that coefficient of that variable is 2. Now I go from the state 4 to 6, because I've added 2 to that. And so that's how you evaluate, or that's how you create this function g. That's what the term is. That is what the new state will be when you apply action x to state s. And then you look at the cost transition function. So what is the increase in the function evaluation due to an action x? Take a variable, what happens? And really you're just looking at what is the difference in the objective function terms between what the inner sum is right now and what the inner sum becomes. Here it's replicated here for this particular solution, for this particular function. Here is the solution and here is our function. Okay, it evaluates at this solution to approximately 2.24. Okay, so let's just go through how you would evaluate this function for this single path, and then we'll talk about how we do it concurrently for all paths. So for a single path, you start at the root. The first state is going to be 0. Now, for this particular path, 1, 0, 1, 1, let's see how, again, we evaluate it. So starting from the root, let's look at the first action that we take. So the state initially is 0. I have now taken the action of including variable x1. The state now moves from 0 to 1. Right, here it is. So Si, so S0 is 0. S1, I guess. Sorry, S0. S1 will equal whatever the coefficient of the variables times the action that you're taking on that set. So it equals 1. Now, what is the function evaluated when the inside of that term is 1? It's the square root of 1, so it's 1. What is the function evaluated when you put in 0? It's 0. 1 minus 0 is 1. That's why you get that coefficient. That's why you get an arc cost of 1. Okay? I'm iteratively calculating what the function equals. Next action is don't take x2. That doesn't affect the state. That also doesn't affect the evaluation of the function. Okay? Because every single functional term, when I plug in 1 and I plug in 1 into the square root function, so up here, you're going to end up just with 0. It gets a little more interesting when you get to the next layer. Consider the next action, which is setting x3 equal to 1. The state goes from 1, which what it was before. That's what fk of x prime equals if I just control on when I just act on these two variables. Now I'm going to set x3 equal to 1. That is going to move the state from 1 to 2. What is the marginal effect on the objective function when I take that action? I am now moving from the square root of 1 to the square root of 2. The square root of 2 minus the square root of 1 is 0.42 approximately. And of course, if I take the sum of the weights from here to here, 1.42, that's what the function evaluates to. One more layer down, it's the same game. I'm taking a variable x4, I'm setting it equal to 3, I go from state 2 to 5, I take the square root of 5 minus the square root of 2, that's what my marginal impact on the objective function is, and then I get what the total weights are. Questions?
Yes. So this again doesn't seem to impose any constraint on the function because I could take the state to be the function value itself.
Of course, this does not.
And the change is just the change in the function value.
Absolutely, which is why I said I'm not really imposing anything, but you will see that if I take any general function, I use your particular DP, which is a valid recursive model. Terrible recursive model, but a valid recursive model, you can build this thing. But suppose you have 10 variables or 100 variables, it's going to blow to 2 to the 10. 2 to the 8.
But why won't this blow?
Because the state, if you are assuming that the coefficients are integer, for example, let's look at a particular layer, and I'm going to show you an example.
Oh, you're saying the total number of sums you get is not always.
And actually it's pseudo-polynomial in this case if you're assuming that they're positive integer coefficients. But even that will be too big, and eventually I'll get into what we do with relaxations. This is just for building it exactly. We cannot build these things exactly for arbitrary functions. This thing grows way too large. It's entirely too complex.
So do we assume that we know the state transitions?
Yeah, well, we assume that we can write that function, yes. You need to have that function, absolutely. Because if you don't have that function, then it's not in our modeling framework, and so you cannot do it. But of course, you know, there's first of all, if it's binary variables, you can easily create something, right? You can just say the state is the binary set, then that's fine, right? And then you just evaluate the function. So it's totally general in that case. But again, the things are going to grow very, very large, and we're going to talk about how to handle that in a minute. Okay, so what's nice about this, and this gets to your question, why is it good to use this recursive model as opposed to maybe what you proposed, but maybe in this case it's the same anyway, I'm not sure. Well, no, it should be different if you just use the binary set to represent the state. This is a little bit better, because now, if any state, we think about it as starting from the root and building downwards, okay? You go from the root, you take every possible action from all the nodes on the layer. So having constructed layer J, I go there and I have all my nodes. I also have a state at each one of those nodes. I think of all the possible actions, and sometimes you can put some constraint information in these things too. Because you might say, if I know the state is 4 here, I actually can't take x1 equal to 1, or can't take x1 equal to 2, based on the constraints in the other part of the problem. So this is where maybe nonlinear constraints can work out. But anyway, that's not what we're doing in this particular body of work. So if I think about it down to this layer above, each one of these nodes are separated, nothing has been combined. If I take the action of including x3 from this path, I get to a state of 3. I'll get the same state from the right path. So I can merge these things together because the rest of the function evaluations will be identical. Exactly identical. And so I can just merge these things together, put the appropriate arg weights, and just continue until the terminal. Eventually everything coincides at the bottom layer. Well, you could just put them together. And then, but oftentimes you're able to get some merging, right? There's a lot of merging going on here because 1, 2, 4, that could be up to 8, right? I'm not imposing any constraints on the variables right here, just trying to evaluate the function. And so, yeah, I mean, it's pseudo-polynomial. In this case, if you have integer positive, well, pseudo-polynomial. Okay, so we can build the diagram, and this is an exact decision diagram. This thing grows very large. We're going to talk about how to deal with that in a second. Okay, so let's take a quick high-level view again. You take your optimization problem, you decompose it. So, yeah.
Could you explain quickly why is, if you don't have positive integer, the size is bigger than pseudo-polynomial?
Well, still, I guess it should still be pseudo if you just take the absolute values thing, because what's the possible partial sums that you get?
I see.
It's going to be at most whatever possible sums you can get there. So, yeah, I mean, you can just take the -1.
Sure.
Just add it and then just see what the possible sums are.
So is another way to see this is the contraction is possible because the level sets of your functions capture a lot of integer points on each level set, and essentially how are you merging things? You're merging solutions when they have the same function value, right?
In this case, yes, but I don't think in general they have to have the same solution values. For this function, yes, for sure. But there may be other functions, actually not necessarily. So there are situations where, for example, suppose I imposed a constraint here that I could take at most 2 or 3 of these variables. Then you can also merge nodes, and this does happen, and in our implementation, you can merge nodes even though the function evaluation would eventually be different, but because of the constraints, you can only include certain combinations of these variables. And that's how we deal with linear functions, linear constraints, when we try to impose them through diagrams. But yeah, in this case I agree, because if you take the sum of the weights to here and the sum of the weights to here, you will get the same thing because of the way that the state is described, and because of the recursive constant, but not in general. But yeah.
So is it true that there will be no mergers if all the coefficients were distinct powers of 2?
Yes, absolutely. We can still handle that, and I'm going to show that in just a few slides. Cool. Yeah. Good. Okay, so high-level view again. Suppose we could build these diagrams exactly for each term. Let's just assume that's possible in the memory space that we have for solving this problem. Okay? We decompose, we build it. I don't really care about what the functional forms are yet. All right? And then we reformulate this as a linear integer programming problem that's probably not too difficult to understand. A decision diagram is really just a, well, longest path, but it's directed acyclic, so it's fine. The shortest path, polytope, if you want to think of it this way. So what do? You reformulate the problem now as a consistent path problem. In this particular paper, we really just take these consistent paths, we dump it into Cplex or Gurobi, I can't remember. Now I'm actually working with a couple people from Clemson on solving this problem in more efficient ways, using some polyhedral analysis. We're getting there. But for this problem, we just dump it into one of these integer programming solvers. And it's not so hard to see. So suppose that I were to build a diagram for each one of these terms. Now, not all of the terms have to have the variables, right? I mean, one term might be on some subset of the variables, one might be on the other one. Here's a particular example where I have one function, f1, and it's defined on x1, x2, x3. This one's defined on x2, x3, x4, x4, and x5. Yeah, they're continuous and all this. It doesn't, I mean, you know, the ordering, but it actually doesn't matter, it's arbitrary. So, what do I want? So if this really represented every single function evaluation for this term, and that one did and that one did, what is the problem I want to solve? I want to find a path in each of these diagrams that correspond on the values of the function, on the x variables. So, I mean, if you look just at this one individually and you optimize, 11 is going to be the longest path, but it shouldn't be so hard for us to understand that that might be suboptimal, right? Because if that's 11, the best thing you can do is 15, because here I've taken 0, 0, 1 for the first 3 variables. That means I have to take x2 equal to 0. And then the best thing I can do throughout, unless I did some math incorrectly, which is possible, is take a value of 15, but it's suboptimal. 21 is the optimal value if you consider all these at a time. So if you want to maximize over all these concurrently, you get an optimal value of 21. This is a network